tell me what this is. If all of those bonds have a hydrogen on the end, what is the name of that structure? What's the name of that structure if all of those have hydrogens on them? Do you agree?
Yeah.
Butane. That's butane. So the formula for that is C4H10. To make that a cyclic compound, this has to now attach to this. Correct? Therefore, in order to do that, you've got to get rid of that H and that H. C4H8. Same thing for pentane, right? When it becomes any of these, when they become cyclic, you've lost 2 hydrogens. So, the question said, general formula for a saturated cyclic compound, because I didn't want you to put in a double bond, because that becomes different from this. So, the general formula then is CnH2n, which happens to be the same as alkenes. Now, if you put in a double bond into that structure, it is now C4H6. That's unsaturated because there's a double bond. So the general formula for that one would be CnH2n minus 2. So when you have a cyclic alkene, it has the general formula of an alkyne. Okay? So cyclic hydrocarbons that are saturated have the same general formula as an alkene because they're missing 2 hydrogens. A cyclic unsaturated compound has the same general formula as an alkyne because there's a double bond and you lost 2 hydrogen, so it's down 4 H's. Any other question you want to take up? The bonus, hybridization of the carbons in benzene. How many, what's the formula actually? What's the molecular formula for benzene? C6H6. C6H6, if you draw that, there's your C6H6. But how many bonds are on those carbons? 3. So they know there's some sort of bond here. And this was very accepted forever. Right? This one or this one. That's supposed to come together. So these two are resonance structures of each other. So the hybridization on this carbon is identical to the hybridization on any of the other carbons, and you have technically 3 sigma bonds and a pi bond. And this is actually how benzene is. It has these 3 electrons, so it's sp2, and then this p orbital. Let me see if I can find you a nice picture. Here we go. Here you go. Here's your sigmas, right? It's trig planar. And then you've got these p orbitals sticking out perpendicular to the plane. So benzene's planar, it's sp2, trig planar. So it's in the plane of this desk. So there's a p orbital on each carbon sticking up, sticking below my desk. So like these. Because you have these p orbitals like you have in graphite, the electrons can move between them. So sometimes they represent, sometimes they represent them as rings, and therefore they show it as a ring in the structure. So that's why this one is the best structure for benzene, because of this delocalized electrons in these p orbitals, and they are just whipping through those. Because they're delocalized, because they're free to move around the ring, they're not available for bonding. And they know, based on X-ray structures, that the bond lengths between the carbons are identical. Single carbon-carbon bonds are longer than carbon-carbon double bonds. So they don't see in the X-ray structure big, small, big, small, big, small bonds. They see 6 bonds that are the same length. So that is why we tend not to draw it like this anymore. We tend to draw it like that. So there's 2 factors, delocalized electrons and bond length. They have the same bond length between the carbons. Okay? But when I said what is the hybridization, you just had to give me the hybridization. You didn't have to show your work. Yeah, it goes into the p orbital. So you don't have that p orbital available for hybridization. How many p orbitals are there? Nope. 3. So if one of them is gone for that pi bond, that leaves only 2 left. So it's sp2.
So we don't, okay, so normally the shape would be sp2 for like the trigonal plane.
It is, yeah.
And then we don't remove from the sp2, we remove from the hybridization. We remove from the 3 p's, not the regular formula, which is sp2. So, like, imagine like if it was a pi bond, and like.
All right, enthalpy. Write an enthalpy change for delta H solution. You're going to have your substance as a solid going to your substance as an AQ. If that substance is ionic, you can write it on the right-hand side as your ions or as the compound. There will be an energy change associated with this change, and it will be based on a mole of that substance. Okay, that will be based on the 1 mole of that substance. Reaction in a bag. Do you remember doing that? Which one got hot when you dissolved it? The balls. Do you remember what the name of that substance was? Calcium something? I don't know how to look that up. Calcium chloride. So, when calcium chloride is dissolved, was that an endothermic or an exothermic reaction? Did it absorb heat or did it release heat? It released. So heat was produced. It's exothermic. So you would have an amount of energy on your right-hand side because heat was produced in that reaction. So, according to Chegg studied textbook solutions, the amount of energy is negative 81.3 kilojoules per mole. The negative sign means it's exothermic. So this is the molar enthalpy. For the dissolving of calcium chloride. So we're going to get into how do we represent this thermochemical data this week. But this amount of energy will be placed two different ways for a thermochemical equation. Right now this is a chemical equation because there's no quantity in there. But for every mole of calcium chloride that you dissolve, you will get 81.3 kilojoules. What's the mass of 1 mole of calcium chloride? How would you figure that out? If I say to you, you take 1 mole of calcium chloride and you dissolve it, you get 81.3 kilojoules of energy released. What was the mass? So, 81.3 kilojoules per mole, or 81.3 kilojoules per 110.98 grams. So it's going to depend, how much heat you actually release will depend on how much of that substance you use. A molar enthalpy of neutralization. You would include the substance. There's 2 possible substances there, and they have different coefficients. You have to be very specific. Okay, so your state the substance as being that is the molar enthalpy of neutralization for. Sodium hydroxide has a different molar enthalpy of neutralization than sodium hydroxide, because they are different substances. Molar enthalpy of formation. We will actually spend a whole entire lesson on this. Molar enthalpy of formation is the energy change associated with the formation of 1 mole of product from its elements. But we're going to come back to that. You will get that definition again later. But molar enthalpy of formation, you have 1 mole of product. So you'll notice the X changes, right? Delta HX, the X changes depending on the types of reactions. So this is your molar enthalpy. And it depends on the substance, depends on the process. The N is for the moles of the substance. This whole relationship refers to our system. So the moles of your substance is going to be the moles of your system. What are you doing? If you're dissolving sodium chloride in water, it is the moles of sodium chloride. If you are combusting propane, it is the moles of propane. And then this can also be written as delta HR. This is the energy change for that reaction. Which is why it sometimes has an R subscript. R for reaction. So this change for this reaction depends on the quantity of the substance that's in our chemical or physical change. So delta H will change, delta HX is a constant. Will you be asked to memorize your delta HXs? Absolutely not. Okay? You won't. You'll be given them in your textbook in a chart. You'll either be asked to find them mathematically, or you would be given them in the question. Delta HX is a constant, and it depends on the substance, depends on the process. Delta H or delta HR is what will change. Remember this relationship? This is this. So our enthalpy change for a reaction is the same. Got it? We want to find the total energy change if 180 grams, so our quantity is 180 grams, it's vaporized. 180, but look at the units here. We've got kilojoules per mole. Delta H is equal to N times delta HX. So what is the units on delta H? What is the unit on delta H? What are the units? Kilojoules. So, molar enthalpy is always kilojoules per mole. Enthalpy change is always kilojoules. How are we going to figure out how many kilojoules of energy are released if we have 180 grams? So what do you get? So I'll let that sink in. 180 grams will release 407 kilojoules of heat. Using appropriate scientific notation, significant digits, it's about 410 kilojoules. What is that for? If you had to write a sentence for this, what would you put in as a sentence to include that amount? What does this represent?
Enthalpy change per mole
It's not per mole.
per
How many moles?
10 mole. The vaporization of water.
Yeah. So the enthalpy change for vaporizing,
10 moles of water.
10 moles. I'll put approximately 10 moles of water is approximately 410 kilojoules. So, the enthalpy change for vaporizing approximately 10 moles of water is approximately 410 kilojoules. What would be the enthalpy change for condensing approximately 10 moles of water? Ah,
Be negative.
yes, it would be negative 410 kilojoules because it is the reverse process, same amount. So you don't have to do another calculation. You know the quantity of energy that is associated with 10 moles of water, but it is the reverse process, so energy will be going out rather than in. So here, vaporization is an endothermic reaction because delta H is positive. A positive number means endothermic. So therefore, when we do the opposite, it will have the opposite sign. So in this case, because we have this negative sign, it is exothermic. So if your delta H is a negative value, it is exothermic. If your delta H is a positive sign, it is endothermic.